All right, gang, MATH6500. The purpose in this video is to look at ways to assess normality of our residuals. But the first thing I want to do, 2 and 3 are specific to 2 and 3 down here. You can see my pen. Are specific to addressing normality issues. I want to revisit the semi-studentized residuals that I discussed briefly in the previous video. Probably the easiest way to calculate those, and I'm just going to call those standardized residuals because I want to store those, is to do the R standard command with R, and we want that of our model. So we do our standardized residuals and we get 55 of those, right? And we can see that the mean of our standardized residuals, of course, is going to be 0 within rounding issues. Now, the main reason I did that is I want to demonstrate a plot where we look at our fitted values over our standardized residuals. I'm losing my voice for some reason. And you can see we get a consistent theme, right? We get the fanning out, where we have, for lower values of x, we have less variance, and for higher values of x, we have more variance. All right, switch gears. Now, let's get into assessing normality. Now, the first way that we would probably assess normality is some things we've already talked about, and I want to review those. The reason being, sometimes people don't watch all the videos, so I found it beneficial to repeat myself sometimes. So anyway, if we're going to look at a couple of quick graphs, one that I would examine for normality would be a box plot. Now, let's see, we're going to get residuals for the model. I'll tell you what, I'm going to be using the residuals quite a bit, so let me just go ahead and just save those as RESID. All right. So first thing I may want to do is look at a box plot of the residuals. And when I see this, a couple things jump off the page to me. First of all, there are no outliers, which would be good. The second thing is if I focus on the median of the outlier or of the residuals, notice that the distance from the median to the highest value to the lowest value, pretty much the same. So that tells me that I have symmetry. Doesn't necessarily mean that we have normality, but we do have symmetry. The next thing I'd want to look at is a histogram of the residuals. And what does that tell us? Again, from a previous video, it tells us that our sample residuals are bell-shaped and symmetric, and by eyeballing the histogram, it appears reasonable that our residuals come from a distribution that is normally distributed. Please, again, do not say, I'm going to ding you if you do, okay? Please do not say that our residuals are normally distributed. We don't know that. The normal distribution, that's a population distribution of all the residuals. We're working with a sample. So this sample residuals appears to come from a normal distribution, but as you're going to find out later, there's a lot more to it than just eyeballing. We have to have a proportion of cases and so on and so forth. So the normal QQ plot, it's relatively easy to create. I would do QQ norm. There are various ways to, did I save the standard? Yeah, I did. And the normal QQ plot really compares the sample quantiles against a theoretical quantile. In plain English, that tells us we're looking at the deviation from the y equal x line, the diagonal line. So what we see here is typically from about -1 to +1, we won't see a lot of variation, but it's typically from -1 down and +1 up that we end up seeing our most variation. In this case, I don't see enough variation to really cause concerns. Again, we're eyeballing this. We're going to get into more formal procedures here in just a second with the chi-square goodness of fit and Shapiro. Yeah, I don't know. Now, in the next video, we're going to dive into the normal QQ plot, and I'm going to teach you probably far more than you ever care to know about how these values are calculated, how they're ordered, how we create these theoretical measurements. So again, from an eyeballing perspective only, I have no concern with normality yet. All right, so now let's move into to inference procedures. Now, inference procedures means we're going to start creating p-values. So what do p-values do? P-values tell us, based on some null hypothesis, how likely it is that our sample data satisfies the underlying probability distribution based on the null hypothesis. Now, the first one that we use a lot is Shapiro. And Shapiro test for our residuals. And again, I saved those someplace, right? Yeah, yes, RESID. And we get a p-value of 0.88. Now, in isolation of knowing what the null and alternative hypotheses are, that's pretty much irrelevant. For the Shapiro-Wilk, the null, or H sub O, is that the underlying probability distribution is normal. The alternative, the underlying probability distribution is not normal. All right, so in this case, our p-value is 0.88. We failed to reject the null, so we can assume that the distribution from which we are drawing is a normal distribution. Now, something I think is kind of cool, and I hope I can do it justice, is the next approach. And this is the approach of using a chi-square distribution to actually look at the proportion of theoretical values versus the empirical values and see if they match up. Now, if I think just in isolation of whatever your job or your interest may be, I think this is just a neat process because it forces us to think more about a normal distribution. But I think it's really cool if you're maybe a high school or college instructor or a professor, or teacher, whatever it may be, because it's something that you can share with your students. Now, first of all, let's think about a normal distribution. All right, so I'm going to try to draw one the best that I can, and that's not a very good one, but pretend it's a good one. Is that a normal distribution? Well, I don't know. Normal distribution is perfectly bell-shaped and symmetric with the mean in the center, and from one standard deviation above the mean to one standard deviation below the mean, we have 68% of the proportion of cases. From the mean minus 2 standard deviations to the mean plus 2 standard deviations, we have 95%, again, assuming we have a normal distribution. Now think about it. You could be bell-shaped and symmetric and have 40% of the distribution from here to here and 80% of the distribution from here to here and still look like a normal distribution, but it doesn't satisfy the proportion of cases. So that's why we dive into this more. So from mu minus 3 standard deviations to mu plus 3 standard deviations. I'll put this down here. We have 99.7% of the cases. Now, from here up, we have, of course, 100% of the cases below below the curve. We've accounted for 99.7% from 3 standard deviations below the mean to 3 standard deviations above. So obviously we have 0.3 left. Because of symmetry, we know that half of that will go here, and we know half of it will go up here. Now, we know that standardized residuals just like z-scores have mean equals 0, standard deviation 1. So this will become a 0, negative 1, plus 1, negative 2, plus 2, plus 3, and negative 3. Now, this leads us into from the mean being 0, from negative 1 to plus 1, we know 68% of the distribution falls, so 34% has to fall here, 34% has to fall there. So from negative 2 to plus 2, we have 68% minus 95, so that's going to be what, 27%? So half of that 27% has to go right here, and half of the 25%, or 27%, of course, has to be right there. Now, from negative 3 to plus 3, we have 99.7%, but we have 95% here, so we're missing 4.7%. Divided by 2, 2.35%. And of course we know the 0.15% from here to here and 0.15% from there to there. All right, so we're going to need that information in just a second. Now, let's come back over and look at our standardized residuals. All right, so the standard deviation of our standardized residuals is 1.009903, which of course is within rounding, equal to 1. And then of course our mean of our standardized residuals is equal to 0, again within rounding errors. Now, if we, not really sure how I want to do this. Okay, the first thing I need to do is if I look at my standardized residuals, and if I look at the range of the standardized residuals, I can see that it ranges from negative 2.1 to 2.26. So about 2.21, somewhere in there, to about 2.26. But nevertheless, for this to be a normal distribution, I want to range this thing from about negative 4 to positive 4 to see if the proportion of cases is the same. Now, you may challenge me on that and say that that 0.15% goes from 3 to infinity. I understand that. But most of that 0.15% is from 3 to 4. And most of the 0.15% down here is from negative 3 to negative 4. So what I want to do is I want to create some bins. And I want to start from negative 4, and I want to go to positive 4, and I want to go by ones. Well, I completely forgot what I was doing. All right. Then I want to come in and get my counts. So I'm going to call those just scores. And I want to use the cut function for my standardized residuals across the bins. Now, if I do a table of the scores, what I can see is the counts from my data set that fall from -4 to -3 and -3 to -2. So I'm going to call those just my counts because I have nothing more clever to call them. Now I want to use the chi-square techniques to see if the theoretical distribution of these proportions that I have over here, the 34%, the 34%, the 13.5%, and so on, match, or I should say, do the counts match the theoretical distribution? So I'm going to just call this residuals. Doesn't matter. So I'm going to use the chi-square test. And I'm going to use my counts, and I'm going to compare it to the probability distribution for the 8 compartments, if you will. So this will be 0.0015, 0.0235, 0.135, 0.34, 0.135, 0.0235, and 0.0015. Now we're probably going to get an error, which we do, and again, go back to, for those of you that have taken 6610 from me and 6620, why do we get an error here? Well, we get an error because our minimum expected cell count needs to be 5, at least 5, and I'm sure it isn't with these 0s and 2s, with the small cell counts there. But nevertheless, let's go ahead with the chi-square test, and we can see that we get a p-value of 0.99. Now, because we violated the assumption of the minimum expected cell count being 5, our p-value, we're inflating the probability of a type 1 error. So our p-value is going to be somewhat inflated. So how much is it inflated? Well, we don't know. But looking at Shapiro being a p-value of 0.88, I'd say because we have violated the minimum cell count assumption, I'd say that we're probably, this test is probably closer to a true 0.88. That would be my estimation, but there's no way to know that, right? Well, there actually is a way to know that, but it's beyond the scope of this video. All right, so I'm assuming that it's less than 0.99, but nevertheless, with the chi-square test, our conclusions, our H sub O here would be the counts follow the theoretical distribution. The H sub A would be the counts do not follow the theoretical distribution. So based on the counts that we get, the 0, 1, 9 in these particular bins, there's no reason to think that this distribution, that this sample doesn't come from a distribution that is normally distributed. All right, I think we are done with this one. Yeah, we are. So the next video is really cool because we're gonna dive into the QQ plot, and again, you're gonna learn probably far more than you ever cared to know about where those values actually come from. All right, take care.